right? So we have our first equation. We got our speed of light related to our frequency and our wavelength. What is another equation? All right. So our other equation is that the energy is related to h times our frequency. Now, what does that h stand for? Planck's constant. Very good. Let's make this a little bit bigger. So that's Planck's constant. Now, the reason why this is so important is that we can use these two equations and we can combine them together, and that's how we get Anthony's equation, right? Is that we can use our C equals lambda frequency. We can solve for that frequency. So frequency is the speed of light divided by our wavelength. And then we can plug that into this one. So it's Planck's constant times the speed of light divided by our wavelength. Now, the important part to remember is that for a wave, right? So a wave could be like for a photon, something like that. If our wavelength goes up, how does that impact our energy? If our wavelength goes up, how does that impact our energy? Does it go up? Does it stay the same, or does it go down? It should decrease. And so when we're looking at our different types of light radiation or electromagnetic radiation, the wavelength tells us a lot of information about its characteristics, including its energy. And that's because they're directly related, or sorry, they're inversely related. So when our wavelength gets longer, our energy is going down. As our wavelength gets shorter, our energy goes up. And so if you think about it, the difference between something like a radio wave versus like visible light radiation that you guys can see versus a microwave, right? They're all the same material, just at different wavelengths, right? So they're all photons, they're all that packet of energy, but they have different wavelengths, and that's what gives them the different energies and gives them the different characteristics, right? So when we worry about X-ray radiation, it's because their wavelength is really small. And because their wavelength is so small, then they carry a lot of energy behind it. So when we're looking through for some of these, let's go ahead and let's tackle this first one. We have an infrared wave, and we measure it at a wavelength of 5.6 times 10 to the 4 nanometers. What is its frequency? So what are we looking for in this problem? What's it asking us to find? Frequency, right? And so which equation do we want to be thinking about? If we have the wavelength and we want to get into a frequency.
Is it the speed of light divided by the wavelength?
Very good. So we're looking at the one that involves our speed of light and our wavelength and our frequency, right? So we have C is our speed of light, we have our wavelength, we have our frequency. So we need to solve for frequency, right? Now, what value do we have for the speed of light? (2.998 times 10 to the 8). And the units for that? Meters per second, right? So we got meters per second up here. And right now, our wavelength is 5.6 times 10 to the 4 nanometers. Now, can we just divide these two values? Will that give us our frequency? Or is there something that we need to change first? So if we're looking at these units, right, we have meters per second, and we have nanometers. The units for frequency is 1/seconds, right? So we need those meters to cancel out. Is that going to happen with our current setup? Are our units canceling out? Not yet. So we have to change our nanometers to meters, right? You can also change your meters to nanometers. It doesn't matter. They're the same thing. So what we need to do is we need to add in another step where we change 10 to the 9 nanometers is equal to 1 meter. And now you can see that our units are going to cancel. Our meters would cancel with our meters, our nanometers with our nanometers, and we'll end up with 1/seconds. So I'm going to go ahead and make a little space here. We need to go ahead and take this. We can add our 10 to the 9 nanometers in 1 second, or not 1 second, 1 meter. And so what's the frequency that we end up with? What is the frequency of that photon? So what do you guys think? What should our frequency be?
Ten to the is that 10 to 17?
Is it 5.4 times 10 to the 12th?
So it is 5.4 times 10 to the 12th. And then what's your unit for that? So you can have it as hertz. You can also say per second. So second minus 1, right? So anytime that it's to the -1, that's basically saying the same thing as 1/. Right? Those things mean the same. Right? It's just one way to kind of write it all without having to do those big lines underneath. Right? And so that's what we're looking for our frequency and our wavelength and how we can move back and forth between them. Right? So if you have a frequency, we should always be able to get to a wavelength. If we have a wavelength, we should always be able to get to a frequency. And that's because the speed of light doesn't change. It's a constant. Right? So that part's not changing. So every light that you see has a given frequency with it, which means that when you see a red light, all of those red lights, if they're the exact same red, they're all going to have the same frequency for them.
Professor Lau.
Mm-hmm.
Good morning, first of all. And isn't this supposed to be 10 to the 13th power? Go up?
I have it as 10 to the 12th.
Because what? Here, I'll explain it. 8 plus 9.
Mm-hmm.
That's meters to seconds to nanometers.
Mm-hmm.
That's 17.
So
Minus 4 from the bottom, so that should be 13, isn't it?
is 2.9 bigger or smaller than 5.6?
Smaller.
So that's why we need to go down one more. Right? Because otherwise what you would have is 0.54 times 10 to the 13.
Yeah, that's what I have.
Right? But that's not the correct scientific notation, right? So you should move this to be 5.4, and that should become 10 to the 12.
Ah, gotcha.
Okay. So let's look at number 3. So we're going to broadcast at a certain frequency, 9.87 times 10 to the 7. And so what we want to look for that is we want to know the energy of one photon of this radiation. So I'm going to give you guys a moment so you guys can figure that part out. So think about what equation you should be using, right? Do we need to change our frequency into anything? Can we use our frequency as it is?
I had a question.
Mm-hmm.
The 9.87 times 10 over 7. So if you put it in hertz, then the decimal moves to 98.7.
So is that just hertz or is that megahertz?
Oh, okay. Gotcha.
Right? And so that's the difference between them. Right? So if you're just doing hertz, it would look the same thing. It just would have, instead of per second, it would just have hertz.
Is there a reason why they converted it to megahertz, or?
So when you listen to the radio, what's your favorite radio station?
Oh, I don't really listen to the radio.
But when you look at those values, right?
Mhm.
Their values are given in megahertz because that's the range that most radio stations happen at for FM, right? So when you have like Tariff 101, right? That's 101 megahertz, right? Or when you're like 95.7 the game, right? That's 95.7 megahertz. And so that's just why they changed it to megahertz, is because that's really what you would report as a radio station is your frequency in megahertz.
Okay. Thank you.
Mm-hmm. And so as you guys are getting this filled in, you can go ahead and put your answer into the chat and we can see how you guys came out. And see if we start to match or not.
Just double checking, Professor Lau.
Mm-hmm.
U is frequency, right?
The little V looking thing, right? That is frequency.
Okay.
Mm-hmm.
Thank you.
Mm-hmm.
And for light, is it okay we say 3 times 10 to the 8, or do you prefer 2.99?
So that depends on how many significant figures you need, right?
Mm,
So if you need more than 3 significant figures, then you should be using 2.998. If you're using 3 or less, then you can use the 3.00.
okay. I'm just lazy. I'm going to use 3.00 then.
In this case, it won't matter because we only need 3.
Perfect. Meters per second.
Mm-hmm.
And
So we should be looking at that frequency, right? So we have that energy is related to Planck's constant times our frequency.
oh, energy. Damn. What is that?
So once you get your answer, go ahead and put it in chat, or you can say it out loud. We can see how we're doing. Now, how many of you guys are stuck, right? So if you're stuck, what you guys can do is in your, well, let's try this. just go ahead and raise your hand. I'm kind of curious to see how many of you guys are stuck, because this is taking a little bit of time, and so I want to just see where we're at. All right. So we got our first answer in, right? Now, you want to double check your math there, because it looks like you have something that's kind of different than what I have. And so make sure that you're not just using 9.87, that you're using the 10 to the 7 as well, right? Because it's the whole frequency. So it should be 9.87 times 10 to the 7 hertz. All right, so we're still waiting. Now, one thing that helps, right, when you guys are doing all this studying, you should just have your equation sheet here. So that way you guys don't have to look up a whole bunch of different things. On our equation sheet, we have the equations, right? So that's under our atomic structure. We also have the constants there. So you have Planck's constant, you also have the speed of light constant there. You also just want to get used to how it's formatted, because that's always going to be how you guys will get your equations from now into the rest of the class, right? So it's good to be familiar with it so you can find your equations pretty quickly. Also, so that you know the correct format for it. All right, so we have 6.54 times 10 to the negative 26. Now that's a number. We should have a unit with it for it to be an answer. So what should our unit be? Joules, very good. So that is what we're looking for, right? And so what we knew was that we had their energy as being Planck's constant times their frequency. Now, Planck's constant is that 6.626 times 10 to the negative 34, and its units are joules second. So it's not joules per second, it's just joules and seconds both on the top. Okay. We multiply that by our frequency, 9.87 times 10 to the 7. And so that's how we can get that 6.54 times 10 to the minus 26. And that should be joules. Now, more specifically, this is going to be joules per photon. So one of those packets of light, as it's going through, carries that much energy. Does anyone have any questions on that part?
I thought that 9.87 was the frequency. So didn't we
So,
need to find the wavelength
so
to?
when we look at our equation, right, we have it as E as h over our frequency. We also have it E is equal to h, the speed of light, divided by our wavelength, right? So you could use either one. It just depends on which version of the equation you used. So in this case, because we were given frequency, we could just use that top one. But if you wanted to, you could take your frequency, you could convert it into your wavelength by using C divided by our frequency in order to get it to our wavelength, and then plugging that back into here to turn it into an energy. But it's just making you go through extra steps, because basically you're turning it into a wavelength, then you're putting that wavelength back in And so you're using it again.
I see. I confused the wavelength with the V. I thought
Yes,
that was
and
S.
that is a common one, is that we mix them up, right? Because they also, not only do they kind of look similar, but sometimes we just get them moving along in the same path, right? So yeah, you just want to pay attention to that part. Perfect. All right. Now, does anyone have any other questions about how we take our energy and turn it into our frequency? So we're going to go off script a little bit here. And so we're going to talk about a hydrogen atom. We're going to talk about the energy levels of a hydrogen atom, right? So if we have the nucleus of a hydrogen atom, all of our different electrons exist in certain energy levels, right? Because it's quantized. So we can have an energy level of n equals 1 for our first one, an energy level of n equals 2, n equals 3, n equals 4, and so on. Now, who has a higher energy? Electron in n equals 2 or n equals 3? What do you guys think? Who has a higher energy? An electron in n equals 2 or electron in n equals 3? All right. So we got a couple for n equals 3. We have one for n equals 2. What do the rest of you guys think? There's like 12 of you in here. We should have more than 3 responses. Plus, it's a great question. It's 50-50, so it's not so bad. Right? So when we think about it, right? When we're talking about higher energies, when you come to an atom, your electron gets attracted to that nucleus. So it's kind of like it falls down into a hole. And at the very bottom of that hole is our nucleus. So the closer we are to the nucleus, the more stable we are, because the farther we fall into that hole, right? So n equals 1 is all the way at the bottom of that hole. N equals 2 is a little bit higher. N equals 3 is a little bit higher. And so the idea behind our energies is the higher up we are in our energy level, the more energy that electron is going to have. Right? So the farther away from the nucleus you are, the more energy you have. That isn't always a good thing, right? Electrons are normally trying to get to the lowest energy possible because they're kind of lazy. So the less energy that they have to have, then the more stable they become, right? And so that's why n equals 1 is more stable, is that it takes more energy for us to pull them out of that hole. So between n equals 2 and n equals 3, n equals 3 has a higher energy because it's higher in the hole. So if we want to move an electron from n equals 2 up to n equals 3, do we need to add energy or do we need to remove energy? So if we want to take an electron and we want to move it from n equals 2 to n equals 3, is that going to take energy or is that going to release energy?
Take.
Take, very good. So we are moving up that hill, right? So just like a rock getting pushed out of a hole, it takes us energy to move it up, right? So it's going to take in energy. Now for electrons, how it gains energy or loses energy comes in the form of a photon. So in this case, for us to move that electron in, we have to shine a light on it. We have to put in that photon, and it's going to absorb it as it goes up. On the other side, if we had an electron, let's say it was up here at n equals 4, and it went all the way down to n equals 1, it was going to emit a photon that has that energy between them. So this is the relationship of why we talk about photons in this class, is because we're using that to talk about our different energy levels of our electrons. Now, for hydrogen, we've given you this constant RH. And what this does is this accounts for the kind of the attraction of the nucleus, the different electron-electron shielding that would happen in a more complicated atom. But it's a constant. It's called Rydberg's constant. And it's basically helping us calibrate our different energy levels through that constant there. So my question for you is, if we want to move an electron from n equals 2 to n equals 4, what wavelength of light do we need to shine on the, we'll say, the atom? Right? So we want to move that electron from n equals 2 to n equals 4. And so we want to know what wavelength that light needs to be.
Professor Lau, is that 10 to the negative 18?
18. Yep. So when we're first looking at that, we need an equation. Whenever you guys have n values, there should be a new equation that we should talk about. Right? And so who has that equation?
Is it on the equation sheet? The delta
It is on the equation sheet.
equals Reinsberg multiplies 1 over, what is that, n initial squared minus
Right.
1 over n final squared.
Very
So
good.
you indicated that this could be sometimes plus, but sometimes minus, but in our case, it's minus.
Right. So the thing that you want to look at, right? The reason why I have you guys practice with your equation sheet is because this is how I'll present your data, right? So I'm giving you an RH value that's positive, and I'm saying that's initial minus your final. Right? This change in this energy is talking about those energy gaps between those different energy levels. Right? So before we start solving this problem, we're going to look at two different criteria. Right? We're going to look from n equals 1, well, n equals 1 to n equals 2, and n equals 2 to n equals 1. Right? So if we're just looking at this part of the equation here, for this first one, that becomes 1 over, and then our initial would be 1 squared, minus 1 over 2 squared. So 1 over 1 minus 1 over 4, which gives us 0.75. On the other hand, if we do n equals 2 to n equals 1, that becomes 1 over 2 squared, minus 1 over 1 squared, so their gaps are the same amount of energy, but one is going to be positive and one is going to be negative. So if we have a positive delta E, is that photon being absorbed or is that photon being emitted? If we need to have a positive change in our energy, is that a photon that's being absorbed or is that a photon that's being emitted?
Emitted.
Right? So when we emit a photon, are we gaining that energy or are we losing that energy?
So is it absorbed?
All right. So if we're emitting it, it will be negative because we're losing that energy. If it's positive, then it's absorbed. And so this is why I like to give you this equation in that format, is because if it's positive, it's letting you know you're absorbing that photon. If it's negative, it lets you know that you're emitting it, right? Other times they will adjust this equation for you because they're trying to give you the energy of an emitted photon. And so they're trying to give you the positive energy. So that way you would, because it doesn't make any sense for you to say a photon having negative energy, right? The difference is whether it's emitted or whether it's absorbed. And so I would recommend that you practice with your equation so you know what it stands for, right? So you know that if you get a negative one, what that means, or if you get a positive one, and also what format it should be in. And so that's the difference between the different kinds of equations, why some of them they have them as being final minus your initial, and other ones they have initial minus your final. Any questions on that part? Okay, so now let's solve this problem. So in this case, what is our n values that we're going from?
2 to 4. 2 is our
2 to
initial
4.
final.
And so 2 is going to be our initial, and 4 is going to be our final. Oh. All right, so we have our delta E as being 2.187 times 10 to the negative 18 joules. We said that our initial was 2, so 2 squared. And so once you do that, let me know what energy you guys get. What should this delta E be? Very good. Right? So we have 4.10 times 10 to the negative 19. Now that's a number. What unit should it be? Joules. Very good. So this is the joules per photon. Now, is our photon being absorbed or is it being emitted or emitted? Absorbed. Very good. Now, is our question just asking us for the energy of the photon?
Wavelength.
Wavelength. So how can we take an energy and turn it into a wavelength?
Energy equals Planck's constant light speed of light over wavelength.
Very good. So if we want to get to our wavelength, then we would get wavelength is either Planck's constant speed of light divided by our energy. If we set that up correctly, you can see that all of our units will cancel, joules and joules, second and second, and we're going to end up in meters.
Yep.
And so what wavelength do you guys end up with? Very good. We included our units this time. We're getting better at this. That's good. So we have 4.85 times 10 to the negative 7 meters. And if we wanted to change that into nanometers, what would that be? (485 nanometers or 484.5 nanometers, either one, right? Both of those would work. Great. Does anyone know what color that would be? Is that going to be red or is that going to be more like violet?
Kind of violet.
Kind of violet. Very good. Right. And so that's what you're using when you guys get to the ones where they're having you look at your different energy levels. Because this is a really type of question. This is a really common type of question that shows up kind of towards the end of the chapter, because it has you guys working with a lot of different things. You have to understand how your energy is related to your electrons, right? Whether you're moving up in the shells or down in the shells. It requires that you have to know whether you're emitting a photon or absorbing it. You have to be able to change it into your energies and then energies back into wavelengths. So it kind of requires a whole bunch of those pieces kind of coming together. And so that's kind of what you want to be thinking about. Was there any other part about photons that you guys wanted to go over?
So the units for wavelength is in nanometers?
So wavelengths can be any type of length. So you can have them in meters, kilometers, nanometers. It all depends on your scale, right? So a lot of things that have like a color that you can visibly see is in nanometers. Right? But things like your radio waves, those are more at like meters. And things that are even longer than radio waves, so like AM, those can start to get into the kilometer range. So it just depends on what type of wavelength you're talking about. So a lot of times what we'll be looking at when you're looking at transitions inside of an atom will be in the nanometer type of range. Any other questions?
And then you said the units for frequency is 1/seconds.
1/seconds, also known as a hertz. So it's how many times we would see that peak or that valley in a second. Okay.
Professor Lau,
Mm-hmm.
I don't know how you guys went over it. I came in a bit late. Did you discuss about quantum numbers?
Nope, we're about to do that right now.
Oh, perfect.
All
I was
right,
about to bring that up.
perfect. So then let's moving on to quantum numbers. So let's go ahead and let's talk about an element here. So someone pick an element, any element.
Aluminum.
Aluminum, very good. Now, aluminum has its electrons, and its electrons are located in a specific region of space, right? Now, the reason why electrons get associated with certain areas is that they are basically trying to be as close to the nucleus as possible, but as far away from each other as possible. So they're kind of balancing those two things. It's kind of like going to a concert and everyone wants to be as close as they can to the stage, right? So the first person that gets there, they get to go all the way up to the front row, right? The second person that gets there, they would need to come up to the front lobe, but now they can't be right next to that person. They got to space themselves out. And so then they move to another part. And so as we get more and more electrons in there, then they all take on different configurations in order to make that happen, right? So one of the first things that we want to do is we should be able to write our electron configuration, because it's basically saying the address of each of those electrons. So what would the electron configuration be for aluminum?
Okay, we give you noble gas configuration, or do you want?
Noble gas is fine, or the longhand, right?
So
You
that
will need to be able to do both for your guys' exam.
so that should be neon.
So we can have it as neon.
That is 3s2,
Mm-hmm.
and that should be 3p1.
Very good. Right. So that's our aluminum. So that's where our electrons are located at. Right. Now, don't worry about commas when you guys list them out. There's not actually supposed to be any commas. You can space them out if you guys can't do the superscripts. But when you guys write them out, make sure that you do have them properly written. Right. So we should have our energy level as a coefficient. We should have the shell as a lowercase letter, and then we should have the number of electrons as a superscript. Right. So that small one up on top. Right. So this is how we describe where they're located at. But all of these electrons are actually what we consider to be waves. So they're kind of like light, where they're packets and they're particles and they're waves. And so they get a list of numbers that kind of describe how they behave inside of what we call the wave function. Right? All that really translates into is that there's a set of numbers that will translate the location of that one electron. So that way we can clarify one electron from another, right? So every electron has a unique set of quantum numbers inside that atom. No other electron can share it, right? So only one of them has it. And so it kind of basically says, these are all of the characteristics to give you the address of that one electron. And so if we're looking for this electron here, this 1 in 3p1, we would like to identify its quantum numbers. So our first one is going to be n. And so does anyone remember what n stands for? So your n is sometimes the orbital, it's sometimes a shell, but what this one is this is our energy level. So kind of like how far away from the nucleus it is. And so in this case, it's going to be 3. It's going to match
Professor,
it's going to match that coefficient. Yes.
what I can't recall, but what is the difference between a shell and an orbital? Because I have orbital listed as m sub l.
Right. So your shell is kind of like the energy level. Your orbitals are sometimes used to refer to the specific orientations that they take within that. So the shape that they have. So that would be the difference between S, P, D, and F.
So orbital is smaller than shell.
So orbital is smaller than shell, right?
Okay.
So when we are looking at L, right, the way I think about L is I think about it as being the shape that the electron configure or the electron cloud is taking, right? It's also called the subshell. And this is going to be your S, P, D, and F, right? So each of those letters stands for a different orientation. Your S kind of looks like a sphere. Your P ones look like dumbbells. Right? That's the one where it has one going up and one going down. Your D1 has 4 balloons. Yeah. And then your F1 kind of looks all crazy, and I've never been able to draw them very well, so we won't worry about it, right? So each letter basically stands for your L. What value gets associated with S? When we think about our L, what value gets associated with S? It's not 2. It's 0. Very good, right? So the way that it works out is that each one of these letters stands for a number. Now, every energy level has an S. So that one is going to be our first one, and that's going to be 0. Starting from energy level 2 and above, they all have a P. And so that's kind of our next one coming in. And so that's why it gets the 1. D is what gets added onto that. So that becomes 2. F is 3. And so basically each time we add in a subshell, it's because that energy level has gotten bigger. And so there's more space for more electrons. That space means that that new subshell has to take on a different shape. And so those new shapes need another letter to describe their shapes. And so they did get a new value. So S is our 0, P is our 1, D is our 2, F is our 3. So if we're looking at SP1, we knew that its energy level should be 3. What should its L value be?
1.
1. Very good. Now, M sub L, this is an orientation. And what that means is that the actual subshells, they have many different options. So when we look at P, how many electrons can a P subshell fit? How many total electrons fit into the P?
6.
6 electrons.
6 electrons. 3.
So each orbital can only hold 2 electrons. So how many orbitals do we have inside of the P?
3.
3.
3. So each of those orbitals kind of gets their own box. And so we want to try to clarify which box it fits in. Okay? And so we have to assign them orientations. And what that looks like, if we were to imagine it, is that one of them kind of goes up and down on the x-axis. One of them goes front and back on the z-axis. One of them goes side to side on the y-axis. And so that's the what the M sub L is telling us. It's telling us which orientation it's going to be in. Is it going straight up? Is it going on the side? Is it going front and back? Whatever it is. So the way I like to think about it is the center one is our 0. And then depending on how many boxes you have a negative one and then you have a positive one. You can kind of think that your ML goes from your negative L all the way to your L. So what that means is that if you are S, you only have 1 orbital, so your ML has to be 0. If you are a D, your L is 2, so you will go from -2, -1, 0, 1, and 2. So you have 5 boxes. Ranging all the way.
Wait, Professor Lau, let's take a step back though. S is, well, I mean, N is 3 in this case. It's because it's because it's on the period 3. So
Yes.
N is determined by periods. The script L, that is 1 is because of what? I
Because
remember
it's in the p orbital, right? Or in the p subshell. So because it's in the p shape, then it needs to be a value of 1.
It's because of the SPDF figures you have here.
So
0, 1, 2,
we are
3.
talking about 3p, right? And so if you are in the 3p, you have to be in the energy level of 3, and your shape is p. And so what value of L stands for p?
So based off this, it's 1. P equals 1.
1. Yes. And so that's why our L value is going to be
The
1.
longest time I keep thinking of it as n minus 1 is the value of L.
So
That's why.
that's your maximum value of L.
Oh, maximum value is n minus 1 for
Yes.
scripted L. But to
Mhm.
determine it, you
You
look
look at what subshell it's in.
So that's pretty much the electron configuration, the last value, which is
Well, it depends on which one you're talking about, right? So we'll get to that in just a second.
okay.
Okay.
And
So
then
now that we're trying to do our M sub L, right? If we had assigned this to a specific box, then we would know where it is. But the tricky part about it is that based on the orientation, it could really be in any of those boxes. We wouldn't really know, right? So when we get to that M sub L, it could be -1, 0, or 1, unless for some reason it was specified otherwise. Now, what I like to do is my first electron in there, I always assign to the -1. My second one, I assign to 0. My third one, I assign to 1. My second one is my fourth one, my fifth one, and my sixth one, right? So that's how they fill in. And so I just automatically assume that that's where they would be located. But in reality, that first electron in there, it could go into any of those boxes because they all have the same energy. So it doesn't really matter which box, it can choose either one. So it's kind of like if you were moving into a dorm and you walked into the first floor, you could choose any of those rooms on the first floor that wasn't occupied, right? And so you could get any of those M sub L values. So all of these are possibilities for that 3p electron. It could be, it has to be 3, it has to be 1, but it could be -1, 0, or 1 for that M sub L. Now for our MS is our spin. And what they account for is they account for in our box whether they are spinning up or spinning down. So what values do we have for MS?
positive half, negative half.
+1/2 and -1/2. So we could have either one, 1/2, -1/2. Now, the key part though to remember about that is that we won't know whether it's +1/2 or -1/2 unless there's a second electron in there. Once one of them is in here, we know that the other one has to be the opposite spin of it, right? So if I were to tell you that you are putting in the second electron into the 4d orbital with an M sub L of 1, what would its quantum numbers be? If the first electron was a positive spin, we should be able to do all 4 of those quantum numbers, right? So we'll walk through this part first and we'll kind of piece them together and then we'll kind of clarify that a little bit, right? So we're putting in that second electron into that 4d orbital with an M sub L of 1, right? So what should our N be for this electron? What energy level is it located in?
2.
So it's the
4 and
second
4.
electron in the 4D, right? So it's going to be a 4 for our N.
Oh yeah.
What subshell, right? So what shape are we putting it into? S, P, D, or F?
D.
We're putting it into the D. And so what is the L value of D?
2.
2. Very good. What should the M sub L value be for this one?
Is it -2, -1, 0, 1, 2,
Right?
positive 2?
So that would be if it was anywhere in the 4D, right? But the problem is specific, right? And so where does it specifically say we're putting it?
Hot, 1, sorry. It
1,
says
right? So it says that we're putting it into this M sub L that has a 1. And our last one is our spin,
if it's positive, is it plus half?
right? So if it was positive, it would be plus half. Now, inside of that box, right? So let's say that we are looking at our 4D, and this is -2, -1, 0, 1, and 2. What we're looking for is in this specific box, we said that there was already an electron in there, and we're putting in the second. What do we know about that first electron?
The first electron in box 1, or what do you mean?
The first electron in that box, because we are adding in the second electron. We know that was positive. So we knew that the first electron was plus 1/2. So if we make our second electron plus 1/2, it would have the exact same quantum numbers as that electron. So it would be taking up all of the same space. And so that doesn't work. So instead of being plus 1/2, what should our value be?
Negative.
It should be -1/2. So every electron should have its own set of quantum numbers. They can't have the exact same ones, right? So it's kind of like talking about a specific one versus the other. Now, your spin is because when you have an electron, pretty much as they're moving, they can create a magnetic field, and one of those magnetic fields will spin clockwise, and one of them will spin counterclockwise. And so the way that they kind of refer to that is they think of it as pointing up, right? So it's spinning up. The other one is spinning down. And so that's how they get a positive and a negative for it. It's really just, if you imagine it as your arrows, whether it's pointing up as an arrow or pointing down as an arrow. The
So
very
it's always
first
a half value.
It's always a half value. It's either positive a half or it's negative a half, but it's always a half value.
And just
So-
to double check, if it's positive half and negative half, doesn't that cancel out?
And so when you put two of them in there, then we don't see the spins.
Yeah.
Yeah.
And by the way, this actually never happens if I'm not mistaken. Don't you have to start with -2 and work your way through to 2 and then come back or something like this?
So no, you don't, right? And so what happens? Let's say that this is your energy level, n equals 4, right? Right now, when we've been drawing our rings, right, we always draw it as just one ring. And so it's this idea that all of that energy in that one ring, like all those electrons on it, have that same energy. But in reality, some of those have a little bit less energy because they're in the S, right? So S electrons feel less electron-electron repulsion, and so they have a little bit less energy in them. They're a little bit closer. And so this is called energy level splitting. Some of them will be split into the P. From there, we can also get into the D, And then because energy level is 4, we also have some that are in the F. And so that one energy level, on average, it lines up with this line. But in more specifics, we can split it between that S, that P, that D, and that F through its energy levels. So each of those shapes has different energies in relation to the other shapes. Now, within that one, all of those orbitals kind of take on that same amount of energy. So it doesn't matter. I always use the p orbitals because they're the only ones that I can really draw. When that first electron comes into a p orbital, it has an option. It can go in this blue one that's top and bottom. It can go into this red one that's front and back, or it can go in the gray one that's side to side. All of those options have the same energy. And so it can choose any of those that it wants to go into. The blue one just happens to be assigned as being a -1. The gray one might be our 0. The red one might be our 1. And so that's why when you get your options, you don't always have to start with the -1, the 0, and the 1. I find it easier, kind of like when I fill in my orbital diagram. So this would be my 3p, my 3s. I find it easier to think of them as being -1, 0, and 1. And I start from the left and work my way over. But you could have started at the middle or the left or the right. It doesn't really matter. Right?
Yeah,
Does
that's
that
what
answer your question?
That's what I remember from last year too, when I took this class. You start from the
So-
left, work your way right, and then you come back for the -1/2, I think.
So let's look at our orbital diagram. So this is a good thing. Oh, we're going to open up a worksheet here.
We're not gonna have to remember the diagrams for the orbitals, are we? Do we need to memorize that? Or
The shapes.
the shapes?
So you
Or
do
like-
not need to memorize the shapes, but you do need to memorize how to fill them in. So I'm going to go
Right.
ahead and I'm going to look at this orbital diagram file printout.
So Professor Lau, I don't remember seeing this on the homework, but are you going to require us to know when compounds are combined and then we have to, I can't
MO
remember.
diagrams, right? So molecular orbital theory where you have to mix the orbitals, that's later on. That's not in this chapter.
Oh, thank goodness.
It still will show up though.
All right.
All right, hon. I'm trying to insert this orbital
We need
diagram
to
here.
know, is it called Vesper? To know how to
You are
draw.
going to need Vesper, but that is later on, so we're not going to talk about it right now.
Okay.
So, oh, come on, rotate.
I thought I missed
So-
something reading.
On one of the lectures, I linked this orbital diagram worksheet. If I can ever flip it, then we could. Don't know why it won't flip. Okay, hold on one second. So what we're going to do is we're going to practice filling in these orbital diagrams. So that way you guys can kind of see what that's like. So let me get this out of the way. All right, very good. So can you guys see the orbital diagrams now?
Yes.
Yeah.
All right. The MS for AL could be either +1/2 or -1/2. It could be either one because we didn't know. So when you're filling in your orbital diagrams, right, there's two rules. Well, there's three rules that you kind of follow, right? So the first one is that we always start at the lowest energy level. So for hydrogen, how many electrons does hydrogen have?
One.
One. And so we're going to put that one electron and it's going to go in that 1s, right? Because that's our lowest energy level. So we're kind of building from the bottom, working your way up. For helium, how many electrons does helium have?
2.
2.
2. So the first one will still go in that 1s. And our second one is going to also go inside that 1s. So before it moves up to the 2s, because the 2 requires more energy, it's going to stay in there and it's going to kind of double up, right? So when it doubles up, both of them can't be face up, right? That would mean that both of them had the same spin, right? They're kind of occupying that same space. And so that won't work for our electrons. So what we need to do is when we put that second one in there, instead of having it face up, oh, come on.
Isn't it supposed to be facing down?
We need to put it face down. So our first one could be face up, and then the second one needs to be the opposite. So it needs to be face down. Right? So whenever we pair up electrons, one of them should be spinning up, one of them should be spinning down. You can do full arrows or you can do half arrows. It doesn't really matter. The half ones are just that little bit easier, right? So for lithium, we have 3 electrons. And so we would do 1, 2, and then we would finally jump up to our next level, 3. How many electrons does carbon have? 6. So we should have 1, 2, 3, 4. And then we get into our p orbitals where we finally have more than one option, right? So instead of partnering them up, right, you want to imagine that you're kind of taking BART, right? So when you guys get on BART, do you immediately take the seat that's next to someone else that's sitting there, or do you get in your own row so you can sit by yourself?
Our own row.
Right? And electrons are kind of like that. They would all like to have their own row first. So they all kind of come in and they spread themselves out into their own row before they're going to partner up. So that's why for our carbon, they have to split themselves apart. And so these 2 electrons should have different m sub L values because they are going into different orbitals. So one of them might be -1, the other one could be 0, right? But they will have different m sub L values. They won't match. Let's look at nitrogen. How many does nitrogen have? 7. Very good. So 1, 2, 3, 4, 5, 6, 7. And oxygen has how many electrons?
8.
8. So when we get to oxygen, what do we need to do to fit that last electron in?
2px down.
Right? So we can need to partner it up with one of them. So we're not going to expand out into this 3s yet. We're going to still fill these ones in, but basically everyone gets 1 electron and then we start partnering them up. Right? So when we go down here to our fluorine, which now has 9 electrons, it looks the same. And then neon. Fills in. And so you can kind of see why neon gets its name as a noble gas as well as helium, is that when they are done, all of their electron spots are kind of filled in. And so that's what we're looking for that part.
So for the example, how come aluminum isn't positive 1/2 then?
So
Because wouldn't it be
it
F?
could be positive 1/2 or it could be minus 1/2.
But I thought you had to start with the up arrows first.
So we start with the up arrows, but the up arrow doesn't have to be positive. So kind of the idea behind it is when that electron's in there, we don't know if it's spinning up or spinning down when it's just by itself. We only know that when there's two of them in there, one of them has to spin up and one of them has to spin down. So it's like we draw them all the same way because it makes it easier. And if you want, you can always imagine the first one as being a positive 1/2 spin, but it's not restricted to being a positive 1/2 spin. It basically could fluctuate up and down. It only gets locked into its position once the other one is there. And so this is something that, like, when they actually try to measure them, what they find out is that as they're doing their spins, sometimes it will measure positive, sometimes it will measure negative, because it will respond to however you measure it, right? But once two of them are in there, then they kind of become locked, because when one flips, then the other one flips. So we always basically have one being positive, one being negative, right? So in the beginning, right, even for myself, when I first started, I always assumed my first one that went in would be in the lowest value of M sub L, right? So I always had it as a -1, 0, and 1 as I would go through. And I always imagined the first one as being the plus 1/2 and the second one as being the minus 1/2. And so that was just how I assigned my quantum numbers when I first started out. As it gets more involved, then you realize that there's more flexibility there, but you won't go wrong if you assign the first one as being your plus 1/2 and your first one into that -1. It just means that there's many different options, right? So the wording that you want to look for is if they say a possible set of quantum numbers, then you need to choose a set. So you should have an n equals, an L equals, an M sub L, and an M sub S, right? And we should just have one set. So we could have like 3, 2, -1, 1/2, right? And that describes a specific electron. If it says all possible quantum numbers, then that's when you would have something like n equals 3, L equals 2, but then your ML, you could have multiple options. And your MS would be both your plus 1/2 and your minus 1/2, right? So it just kind of depends. And it's because all of your MLs have the same energy and all of your MSs have the same energy. So they could go positive or they could go negative, or it could be in -2, -1, 0, 1, or 2, because they all have the same energies. All right. So I appreciate you guys coming out. We do have another review session tomorrow, right? So we'll have it tomorrow afternoon. And so we'll go through more of those as well, if that's something that you guys are interested in. I know quantum number is a little bit complicated, right? But do the best that you can. What I would say is start off by just practicing, do your electron configuration, and then choose one of those electrons, write out its quantum numbers, right? And so you should be able to do your N, your L, your M sub L, and your M sub S, right? The other one is if you take a set of quantum numbers, we should be able to translate that back. So this becomes our 3, our L is our D, and so then this one would be one of those electrons in that 3D orbital. Any questions on that part?
Wait, your script L is 2. Isn't that supposed to be P?
So 0 is S, 1 is P, 2 is D.
0.
Right, so always starts with 0.
Yeah, sorry.
No problem.
Yeah, so it would be.
Okay, you guys. All right, so if you're in the Tuesday class, then I will see you guys in just a couple minutes here. Have a good one.
What time tomorrow? Sorry.
Tomorrow, I believe it's at, I can't remember off the top of my
12
head.
p.m. I think.
1 p.m.?
12 p.m. I think.
12 p.m. Yeah, so noon tomorrow. All right.
Thank you, Professor.
Professor Lau.
Not a problem, you guys. Thanks for coming.
Have a good one.
Have a good one.